magnetism related. Electric charges travel as an electric current in a circuit. Magnets are surrounded by a magnetic field. Moving electric charges produce a magnetic field. A changing magnetic field produces an electric current. Electric current. What would your life be like if you had no electrical energy? Lamps, computers, stoves, flashlights, cars, and all other things that use electrical energy would be useless. What would schools, dentist's office, and stores be like? Hardly a minute goes by each day without electrical energy affecting your life. Recall that atoms have a central nucleus surrounded by a cloud of electrons. The nucleus has protons with positive charges and neutrons with no charge. The electrons have negative charges that are held around the nucleus. In most atoms, the number of positive and negative charges are equal. For that reason, atoms usually have no charge. In some materials, such as copper, electrons are not tightly held by the atoms. These electrons can move from atom to atom. This flow of electrons causes an electric charge to move along atoms. For example, when you turn on a light, electrons start flowing through the wire in the lamp. All electrons have negative charges, so they repel or push away from each other. When the electrons from one atom flow to the next atom, the repelling effect pushes the electrons in the second atom to the next atom. This process continues as electric current. An electric current is a flow of electric charge in a material. A material that allows electrons to flow easily through its atoms is a good electrical conductor. Copper is a good conductor. This property makes copper a good choice for electrical wires. In other materials, called insulators, electrons do not move easily. Current does not flow easily in an insulator. Rubber is a good insulator. Electric circuit. Electric current can flow only when it can travel in a complete path back to its starting position. An electric circuit is a closed path along which current can flow. A simple circuit must have a source of electrical energy, such as a battery. A circuit also needs a wire or other material through which the current can flow. Many electric circuits also have a switch. When the switch is open, a break in the circuit prevents the flow of current. A device such as a light bulb that can change the electrical energy to a useful form of energy is also part of a simple circuit. The wire inside a light bulb resists or slows the flow of electrons. This resistance causes electrical energy to change to thermal and radiant energy. The result is the light you see when electricity travels through a light bulb. The energy source in a circuit provides the push that moves electrons through an electric circuit. Volts measured how strongly the electrons are pushed. Electric stoves and a few other home devices use 220-volt electric current. Toasters and most everything else in your home use 110-volt current. Using the wrong amount of volts can damage an electric device. Series circuit. A series circuit has only one path along which current can flow. Current flows from the negative side of the battery through each side of the light bulb and back to the positive side of the battery. If you remove a bulb, the circuit is broken and the other bulb will go out. Parallel circuit. A parallel circuit has more than one path along which current can flow. Homes and businesses use this type of wiring. If one bulb is taken out, the other bulb still glows. The current still has a path along which to flow. Magnetic fields. Have you ever played with magnets? If you did, you probably know that each magnet has a north pole and a south pole. As you can see in the picture below, if you bring opposite poles of two magnets together, the magnets will attract or pull toward each other. If you bring similar poles together, the magnets will repel or push away from each other. The space around a magnet in which the magnet can exert a force on the other magnet is called a magnetic field. The field is strongest at the poles. Magnets attract or repel because of their magnetic fields. Not all materials can be magnetic. The movement of electrons about the nucleus of an atom causes each atom to be slightly magnetic. For most materials, the magnetic fields face in every direction and cancel each other out. But in some materials, such as iron, cobalt, and nickel, the magnetism of the atoms is stronger. The atoms line up in groups called domains. A magnetic domain is a large number of atoms with their magnetic fields pointing in the same direction. Each magnetic domain is like a small magnet with a north and a south pole. If the domains are pointing in different directions, the material is not a magnet. Some materials can be made into magnets. If they are placed in a magnetic field, their domains will line up with the field. The materials will then be magnets. What do you think would happen to a magnet if you broke it in half? Would you have a North Pole magnet and a South Pole magnet? If you break a magnet in half, you don't end up with a North Pole magnet and a South Pole magnet. The magnetic domains still point in the same direction as the original magnet. You end up with two smaller magnets, each having a North and South Pole. Earth as a magnet. All compass needles align in a north-south direction. Did you ever wonder why? In 1600, an English physician, William Gilbert, suggested that the reason is because Earth acts like a giant magnet. Imagine a giant bar magnet running through Earth. Earth is surrounded by a magnetic field, similar to the field around a bar magnet. The poles of the imaginary magnet are located near, but not exactly at, Earth's geographic poles. You can imagine lines of magnetic forces that start inside Earth and push out from the South Pole. The force lines circle around the North Pole. A compass points to Earth's magnetic north and south. Electromagnets. People have known about magnetism for more than 1,000 years, but in 1820, a teacher made an amazing discovery. One night, the Danish physicist Hans Christian Ørsted was showing his students an electric current in a wire. He had a magnetic compass nearby. He noticed that each time the current was turned on, the needle in the compass moved. Ørsted already knew that a compass moves if it is in a magnetic field. He had just found out that moving electrical charges create a magnetic field. The relationship that Ørsted discovered is known as electromagnetism. All electric charges are surrounded by an electric field. If the charges are moving, they are also surrounded by a magnetic field. This property is useful for making strong magnets called electromagnets. How does electromagnetism work? The magnetic field around a wire that is carrying current circles around the wire. If the wire is shaped into a coil, the overall magnetic field is like the field around a bar magnet. You can make the magnetic field stronger by adding more coils or by putting an iron core into the coil of wire. As current flows through the wire, it magnetizes the iron. This adds to the magnetic field. Using electromagnets. Electromagnets are very useful because the current in the wire can be controlled. It can be turned on or off. Electromagnets only attract magnetic objects when the current is turned on. This property is used when large magnets and cranes move heavy loads of metal. Turn on the current and the magnet picks up the metal. Turn off the current and the magnet releases it. You probably use electromagnets very often. Televisions, CD players, and radios use electromagnets to change electrical energy to mechanical energy. The mechanical energy is used to make sounds by causing the speaker to vibrate. Fans, hairdryers, computers, and anything else with an electric motor uses electromagnets. Electric motor. An electric motor is a device that changes electrical energy to kinetic energy. One common kind of small motor is composed of a permanent magnet, an electromagnet, and a device that changes the direction of the electric current flowing through the electromagnet. When current passes through the electromagnet, each pole is attracted to the opposite pole of the fixed magnet. This causes the electromagnet to turn. Just as the unlike poles line up, the direction of current in the electromagnet reverses, and two poles of the electromagnet reverse. Because two like poles are now near each other, they repel each other. This causes the electromagnet to keep turning. The current in the electromagnet constantly changes direction after each turn. Changing magnetism into electricity. Ørsted had shown that moving electric charges produce a magnetic field. The natural question then was whether a magnetic field could also produce an electric current in a wire. In 1831, the English scientist Michael Faraday showed that the answer is yes. Electromagnetic induction is the process in which a changing magnetic field produces an electric current. If you move a bar magnet through the center of a wire coil, the wire experiences a changing magnetic field. This produces a current in the wire. Moving the magnet faster produces a stronger current. You can also produce a current by moving the wire and keeping the magnet still. Electromagnetic induction is used to produce almost all of the electrical energy for homes, schools, and work. Study the concert picture to see how electrical energy can be changed to other useful forms of energy. Generators. A generator is a device that changes mechanical energy into electrical energy. The two main parts of a small generator are a permanent magnet and a coil of wire. A source of mechanical energy causes the coil to spin in the field of the magnet. As the coil spins, an electric current is produced, and the direction of the current changes. A current that regularly changes direction is called an alternating current. Sometimes a turbine is used to turn the coils in generators. A turbine is a wheel attached to a rod that attaches to the coil. Water, steam, and other sources of energy are used to make the turbine move. Study the picture to see how a generator can produce electricity to run a concert. I want you guys to read through that and then do number 1, 2, and 3. Number 1, make diagrams of a series circuit and a parallel circuit. Then use arrows to show the flow of electricity through each circuit. Number 2, answer why does the coil have to spin in a generator? And number 3, use the internet to learn how fossil fuels and water are used to power plants as a source of mechanical energy for generators. Number 3 is interesting because we did the essays about the ANWR and all the different types of energy we could be using instead of having to use ANWR for resources. So number 3 would be something interesting to do and find, and we can add that to our papers.